Welcome to the course Artificial Intelligence in Oil and Gas. This program is designed for field engineers, reservoir modelers, and digital leaders. It includes 7 core modules: Introduction to AI, Data Infrastructure, AI in Seismic Interpretation, AI in Reservoir Modeling, which will be the focus of this project, Drilling Optimization, Decision Support Systems, and 7, Ethics in AI. Throughout the course, you will gain insights into how AI technologies are transforming workflows across the oil and gas sector. As part of the current learning program, we'll now dive into the contents of one specific module, Reservoir Modeling with AI. This module focuses on applying AI to accelerate and improve the accuracy of reservoir simulation models. We'll explore techniques like surrogate modeling, ensemble Kalman filter-based history matching, and AI-driven forecasting workflows. The technologies covered include machine learning regressors, neural networks, and Bayesian optimization. These tools are used in practical scenarios such as screening development strategies, planning injection, and forecasting capital expenditures. By combining geological understanding with AI, we aim to make reservoir simulation not only faster, but smarter. Let's now take a closer look at AI-driven reservoir modeling, one of the most transformative applications of AI in the oil and gas industry. By definition, this approach uses machine learning and AI to automate the evaluation of reservoir properties and enable accurate forecasting. In essence, it serves as an alternative or a powerful complement to traditional full physics simulators. It leverages historical simulation data and field measurements to produce real-time predictions. The core tech stack includes various types of neural networks like AN, RNN, and CNN, along with gradient boosting trees, the ensemble Kalman filter, and variational autoencoders. Practical use cases span from scenario screening and forecasting under changing conditions to injection optimization and capital planning. This AI-driven approach enables faster iteration, better adaptability, and ultimately more informed decision-making in reservoir engineering. Now let's talk about surrogate reservoir models, a powerful AI-driven alternative to traditional simulation. By definition, surrogate models are reduced-order models trained on high-fidelity simulation outputs. These models dramatically reduce computational cost while preserving predictive accuracy. The typical workflow begins with running multiple simulations using engines like CMG or Eclipse. Machine learning models such as artificial neural networks, XGBoost, support vector regression, and ensembles are trained on the simulation results. Key input features include porosity, permeability, water saturation, pressure, and flow rates, while outputs typically include oil and water production, pressure maps, and cumulative oil. In terms of applications, surrogate models are used in uncertainty quantification through Monte Carlo simulations, real-time optimization, and interactive dashboards. These methods are already being applied in major industry projects, including those by Aramco, Petrobras, and Shell, proving their practical value in large-scale reservoir management. One of the most critical challenges in reservoir modeling is minimizing the mismatch between simulated and actual production and pressure data. This process is known as history matching. With AI, we can now automate and optimize history matching using advanced techniques like the ensemble Kalman filter, particle swarm optimization, deep learning regression, and Bayesian inference. These tools allow us to calibrate multi-well models in a fully automated fashion, integrating logs, field data, and geologic models. The result is enhanced adaptability and the ability to update models in near real time. The benefits include significantly improved permeability and porosity maps, better forecast confidence intervals, and overall lower root mean square error in model predictions. Let's now compare traditional reservoir simulation with AI-based approaches across several key criteria. First, computational time. Traditional simulations can take anywhere from 2 to 14 days, while AI-based models can deliver results in less than 10 seconds. Second, scenario capability. Conventional methods allow for 10 to 50 cases, whereas AI enables thousands of scenarios due to its speed and automation. Third, engineer dependence. Traditional workflows are highly dependent on human intervention, while AI reduces this burden to a medium level through automation and guided workflows. Next, explainability. While traditional models are more interpretable due to their physics-based nature, AI approaches are improving and now offer medium levels of transparency. Update speed is another key differentiator. AI allows near real-time updates, whereas traditional methods are often slow and manually intensive. Finally, CapEx impact. AI delivers a high return on capital efficiency by dramatically accelerating speed to insight, which directly supports more agile investment decisions. In this project, we actively leveraged a set of powerful generative AI tools to streamline content creation and visualization. The process is intentionally non-linear. These tools are used iteratively and synergistically. Importantly, AI doesn't replace expertise. It amplifies productivity and helps accelerate development. We use ChatGPT for generating technical content, crafting scripts, and summarizing complex ideas. MidJourney played a key role in producing high-quality illustrations, including visual metaphors and digital schematics. And finally, Synthesia was used to create narrated video presentations using AI avatars. Our workflow followed a creative loop, from idea to prompt, followed by generation, review, iteration, and finally refined output. This method has proven both efficient and scalable, especially for educational and technical communication in oil and gas. As we integrate AI tools into oil and gas workflows, it's essential to address the ethical risks that come with automation. These include reliance on black box decision models, bias in training data sets, and the overuse of automation without critical human oversight. To mitigate these risks, we apply a responsible AI approach. First, we implement expert-in-the-loop validation, ensuring human review at key stages. Second, we disclose all AI-generated elements to maintain transparency. Third, we emphasize explainability, using interpretable models whenever possible, also known as XAI. And finally, we position AI not as a decision maker, but as a learning accelerator and augmentation tool. This ethical framework helps us use Gen AI confidently and responsibly in industrial settings.